Important physical properties relate to the spaces between soil particles. For a better understanding of soil pore space, this video will work through a series of related properties beginning with soil density. We begin here because the density of soil, its mass per volume, is related to the amount of empty space in the soil. I'm Dr. DeBusk, and this video describes other physical properties of soil such as density, porosity, permeability, and soil structure. One could ask how much soil would weigh if there were no pore space. This is particle density, PD, the density of solid particles only. As an example, the PD of a soil made wholly of quartz sand would be the same as that of a solid block of quartz. Particle density varies according to the type of minerals in the parent material and the amount of organic matter in the soil. The table lists the density of several soil-forming minerals. Note that the densities are very similar. In fact, there is surprisingly little variation in the PDs of most mineral soils. PDs in mineral soils average about 2.65 grams per cubic meter, a value used as a standard in soil calculations. Because soil contains pore spaces, the actual density of a soil is less than the PD. This measurement is bulk density, BD, or the mass of a volume of undisturbed oven-dry soil. To measure BD, a core of soil of known volume is carefully removed from the field. The soil core is then dried in an oven at 105 degrees Celsius until it reaches a constant weight. This is called oven-dry soil. The core is then weighed and BD is calculated. The example that follows is for a core of 500 cubic centimeters that weighs 650 grams. By dividing the weight by the volume, you get a BD of 1.3 grams per cubic centimeter. The BDs of mineral soils depend mostly on the amount of pore space in the soil, because particle weight is fairly constant. Since BD says something about pore space, which is important to plant growth, BD is used as an indicator of soil quality. The higher the BD, the less the pore space. BDs of the topsoils of typical undisturbed, uncultivated mineral soils range from 0.8 to 1.2, but become higher when cultivated. Compaction raises BD. And when typical soils reach a BD of 1.6 or higher, root penetration into the soil is inhibited. Severely compacted soils can reach a density of 2.2, nearly that of concrete, 2.4. The BDs of organic soils are much lower, with values of 0.1 to 0.6 being common, while soils rich in sand are naturally of higher density, with values reaching up to 1.8. In general, increases in bulk density caused by soil usage is a strong indicator of reduced soil health for root growth, reduced aeration, and reduced water infiltration. Total pore space is a measure of the soil volume that holds air and water. This value, usually expressed as a percentage, is known as soil porosity. Thus, a soil with a 50% porosity is half solid particles and half pore space. Porosity can be measured by placing an oven-dry soil core in a pan of water until all the empty pore space is filled with water. The water volume, which fills the pore space, divided by the total core volume, is porosity. The water volume, of course, would be difficult to measure directly. However, the metric system defines 1 cubic centimeter of water as weighing 1 gram. Thus, if one measures porosity metrically, water volume and weight are the same. Therefore, the difference in weight between the dry and the wet cores is the total pore space. This number is converted to a percentage to get porosity. The soil core, used as an example before, had a volume of 500 cubic centimeters and weighed 650 grams when dry. When wet, the same core weighed 900 grams, therefore the porosity is 50%. Texture affects soil pores. The top line in this figure shows total pore space in the soil. Clay has the greatest total pore space. The lower line shows space in large pores. Sand has the most large pore space. The amount of small pores lies between the two lines. Clay has the most small pore space. Loam has a balance between large and small pores. Permeability is the ease with which air, water, and roots penetrate through soil. In highly permeable soil, water infiltrates soil rapidly and aeration keeps roots well supplied with oxygen. Roots grow through permeable soil with ease. We can think of permeable soil as being loose and impermeable soil as being tight. Permeability depends partially on the number of soil pores, but it depends more on the size and continuity of the pores. The movement of air, water, and roots can be likened to walking through a maze. If paths are too narrow, progress is difficult. Progress is even more difficult when most paths come to a dead end. Like a maze with dead ends, soils lacking large continuous pores limit the flow of air and water. Large continuous pore spaces in the soil, or macropores, occur between large particles. Therefore, the number of macropores depends on texture, with sand having more macropores and clay having fewer. Heavy soils would make very poor root environments, except that structure can alter the effects of texture. Structure refers to the way soil particles clump together into large units. These large units are called soil aggregates. Aggregates that occur naturally in the soil are called beds, whereas clumps of soil caused by tillage are called clods. Beds are relatively large, ranging from the size of a large sand grain to several inches. Spaces between clay particles may be tiny, but the spaces between beds may be large. Inside the beds are small water-holding micropores. Between the beds are large, air-filled macropores. Well-aggregated soils contain large continuous pores that promote good air and water movement and that provide easy pathways for root growth. Good water-holding capacity is maintained within the beds. Soil aggregation improves soil fertility and quality by its functions. By improving permeability, it promotes root growth, soil aeration, and infiltration of water into the soil. Carbon inside the soil aggregates is protected from rapid decay, so it preserves soil organic matter. Aggregates can hold plant nutrients near plant roots. Finally, aggregation stabilizes soil against water and wind erosion by improving water infiltration and generating larger particles that move less readily in wind and water. The degree of soil aggregation is an indicator of soil quality. Sand behaves as individual grains, so very sandy soils seldom have much structure. These soils are called single grain. Sandy soils are naturally permeable, so single grain soils have good infiltration rates and aeration. Finer soils lacking structure are a solid mass stuck together like molding clay. These massive soils, as they are called, lack permeability. Massive soil is typical of some sea horizons. Tillage and compaction of wet clayey soil may result in massive soil in the A horizon. This is one of the reasons for another axiom of soil management to stay off wet soil, especially fine textured ones. Never till them when wet. Granular structure is commonly found in A horizons. Beds are small, rounded in form, and considered the most desirable of structures. It increases total pore space and lowers BD compared with a soil lacking structure. Platy structure is usually found in E horizons. Beds are large but thin, plate-like, and arranged in overlapping horizontal layers. The arrangement makes discontinuous pores that reduce penetration of air, water, and roots. Soil compaction can create platy structure in the A horizon when granules of topsoil are crushed into thin layers. Blocky structure is typical of many B horizons. Beds are large and block-like in shape. Blocky structure has medium permeability. Prismatic structures tend to occupy the lower B and C horizons. Beds are large, forming angular columns that stand upright in the soil. Prismatic structure is moderately permeable, whereas columnar structure is slowly permeable. Soil structure forms through a two-step process. The first creates a loose bed, and the second cements it. First, a clump of soil particles sticks loosely together to form a loose aggregate that is weak and easily crushed. This is usually by a process of localized compression. Second, weak aggregates are cemented to make them distinct and strong. Clay, iron oxides, and organic matter may each act as cements. In most soils, microorganisms provide the best cement. When soil microbes break down plant residues, they produce gums that glue beds together. Biological cementation tends to glue the granules of the A horizon, while chemicals cement the blocks and prisms of the B horizon. Organic materials of an intermediate stage of decomposition function best as cement aggregates, indicating the need for repeated additions of organic matter. Maintenance of good granular structure in the topsoil depends on a continuous supply of fresh organic matter, as does aggregate stability. Hence, another rule of soil management: maintain and improve soil organic matter content. Soil users should keep in mind that structure is not a permanent feature of the soil. It can be degraded by mismanagement, like frequent tillage with no additions of organic matter, or it can be improved by certain cultural practices, for instance, planting a grass cover. Grasses are particularly good at creating structure. Good structure is one of the important criteria for soil quality, and to some degree is under the control of soil users. Soil consistence refers to the behavior of soil when pressure is applied. It relates to the degree that soil particles stick to one another or other objects and mostly results from certain types of clay. The effect of consistence can be best explained by some examples. Loose sand, for instance, shifts easily under pressure so that vehicles may get stuck in dry sand along a beach. Preparing a seed bed for planting is another example. A grower wishes to break apart large chunks of soil to get a fine surface to plant seeds in. It is the consistence of the soil that determines how easily those chunks can be broken down. By rating a soil for consistence, one can infer such information as suitability for plowing, likelihood of erosion, or texture. The field test for texture works because of consistency of different soil textures. Often loose soil is coarse textured and friable soil is medium textured or well aggregated. Friable means that soil materials can be crushed easily under pressure. Firm soil is tight or fine textured and may lack good structure or be compacted. Tilth is a general term for the physical condition of a tilled soil. It suggests how easily the soil is to till, how good a seedbed can be made, how easily seedlings can come up, and how easily roots can grow. Tilth is actually a combination of other physical properties, including texture, structure, permeability, and consistency. We may think of it as the physical condition of the soil. Tillage improves soil tilth for a time, improving soil-air-water relations for new seedlings. It does so by loosening the soil and stirring air into it. Fine texture soils are most improved by tillage because coarse soils are already well aerated and loose. Tillage tends to cause a year-by-year decline in soil structure, however. Compare the topsoil of a cultivated field with that of a nearby fence row that has not been cultivated. Beds from the fence row will be more numerous, stronger, and of a better type. The weakening structure of the tilled soil in turn lowers water infiltration, aeration, and ease of root growth, signs of degrading soil quality. As a side note, the physical condition of about the top 3 inches of soil is of particular importance. It is this zone that dictates the rate of water infiltration, which in turn affects how much water will end up in the soil for plant use or how much will run off, causing erosion and transport of pollutants. This is also the zone where seed germination and initial root growth occurs. So here is another rule of sustainable soil use. Pay particular attention to physical condition of the top 3 inches. Compaction results when pressure is applied to the soil surface. Light compaction in aggregated soil squeezes soil aggregates together, reducing the size of interped pores. Further compaction begins to crush the aggregates. Compaction reduces porosity and permeability. Compaction increases soil strength, the degree to which a soil can resist movement owing to pressure. Compaction therefore increases the resistance that roots must counter when they grow through the soil. Other unfortunate results includes reduced air exchange causing oxygen content to fall and carbon dioxide to increase, decreased infiltration of water, increased erosion and pollutant transport associated with greater runoff, loss of nitrogen due to lower oxygen through the creation of nitric oxide, a greenhouse gas, and reduced water percolation, which can leave soils excessively wet. There are several other factors that improve the physical properties of soil. Plowing tends to create large aggregates as it flips the soil over. However, other tillage operations, such as cultivating, tend to crush soil aggregates. High-speed rototillers are especially destructive because they batter aggregates apart. Tillage destroys aggregates by increasing organic matter oxidation and smashing the now weakened beds, so you should till as little as possible. Working in wet soil, especially clay, can increase clotting and puddling, the conversion of aggregated soil into massive soil. It is done on purpose in some rice paddies, canals, and reservoirs to keep water from leaking away. After tillage, raindrops can break apart beds, causing the surface to harden into a crust, especially with soils high in clay. This can reduce yield or seedling emergence. Keeping the soil covered with vegetation or mulch and maintaining aggregate strength are more effective solutions. Or put as another soil management rule, avoid bare soil. Improving tilth is largely a matter of improving structure and avoiding compaction or crusting. The following practices can help protect or improve tilth. Never work wet or quite dry soils. Avoid unnecessary traffic over the soil and drive in the same rows using equipment with the lowest practical weight. Reduce the number of tillage operations or use conservation tillage. Deep plowing or subsoiling can break up hard pans, but the benefits may be short-lived. Keep the soil covered by vegetation or mulch. You can incorporate grasses into a crop rotation to improve structure. In Florida, bahia grass is used as a rotation crop to improve soil. Frequently add organic matter to the soil or grow green manure and cover crops. To micropores and macropores, we could add a third type of soil pore, large continuous channels that begin at or near the surface and lead deeper into the soil. These may be created by cracks in the soil, but more often are biological in origin. Earthworms create the most of the channels as they drag food from the surface into the burrows, and decayed roots leave soil channels behind. These channels caused by soil life are termed biopores and are very important in undisturbed soil. Biopores greatly enhance soil aeration and water infiltration. Any layer of hardened soil is called a pan. Pans restrict deep rooting of crops and deep percolation of water and can be a serious hindrance to cropping. Water may also perch atop such layers, hindering drainage and causing saturation in the root zone. Pans can also promote soil runoff and erosion. The increased runoff may carry agricultural chemicals off the field, contributing to water quality problems elsewhere. There are a variety of types of pans, formed mostly from clay. Soils in the growing regions of the world maintain a temperature balance over the growing season that is satisfactory for plant growth. Soil temperature depends on several interacting factors of energy inputs of sunlight and air temperature, soil's absorption and conductance of heat, and loss of heat at the surface. Soil temperature varies according to the amount of soil energy absorbed. Dark-colored soils absorb sunlight energy readily, while light-colored soils reflect a greater proportion of sunlight and remain cooler. Any material covering the surface also affects light absorption, including turf, mulches, or crop residues, or shading from above by crop or tree canopies. During the summer, deeper soil is cooler than surface soil, while in the winter it is warmer. Certain mulches also insulate the soil surface, reducing heat conductance into and out of the soil. It takes much more energy to warm wet than dry soil. As a consequence, dry soil warms up much more quickly and reaches higher soil temperatures than does wet soil. One practical effect is that sandy soils, which hold less water, warm more quickly in the spring than finer texture soils, and so can be planted earlier in the year. It is important for growers of produce that receive better prices when they get to market sooner. Soil temperature is critical to growers because it affects seed germination and root growth, as well as water and nutrient availability and biological activity. Each plant species has a range of proper temperatures for germination, with a minimum below which seed does not germinate, an optimum for best and most rapid germination, and an upper range. Weed emergence also responds to soil temperatures. For instance, in turf, the timing of pre-emergent herbicide application depends on soil temperature. Root growth also depends on soil temperature, with species-specific responses. Warm season crops such as corn or tomatoes grow best at warm soil temperatures, while peas and other cool season vegetables prefer cooler temperatures. In addition, soil temperature influences the availability of nutrients and the ease of water uptake for plants. Soil temperature also has an effect on the biological activity of soil microorganisms. Below about 40 degrees Fahrenheit, most are essentially dormant. Soil temperature responds to natural conditions that growers have little control over, such as light intensity and air temperature. Some soil manipulations can raise spring soil temperatures, such as plowing in the fall, improving drainage, and planting on ridges. However, the most effective means of managing soil temperature is mulching. Growers use mulch to hold moisture in the soil and suppress weeds, but mulches also affect soil temperature. Organic mulches, such as plant residues left on the soil surface, straw, leaves, or wood chips, conduct heat about 10 times more slowly than soil, and so have strong insulating properties. They moderate soil temperatures, keeping it cooler during the day and warmer at night, but reducing average soil temperature during the summer. Inorganic materials mostly include gravel of various kinds, which conduct heat easily and have little insulating value. Plastic sheeting tends to raise soil temperatures. The temperature of black plastic rises dramatically under sunlight, and some of that heat is conducted into the soil below. Growers of heat-loving, high-value vegetables often plant through black plastic laid out on the ground to increase soil temperature, promote growth and productivity, suppress weeds, and shorten time to harvest. Soil temperature, of course, affects soil and plants in natural ecosystems as well. Some plants from cool, moist climates do not tolerate warm soils well, which has implications for landscape plants. In Minnesota, Colorado spruce is popular and widely planted, but is always under stress and short-lived in this urban soil, which is warmer than its native high-elevation habitat in the Rockies. An interesting case that exemplifies several temperature principles is fire. Fire is present and even necessary in many natural ecosystems like prairies, the brushlands of the West, and some forests. Fire heats the soil directly, but after effects are usually more important. With the dense vegetation and organic residues above the soil surface now thinned and removed, more light reaches the soil surface. The soil is now covered with a layer of dark ash, which absorbs sunlight. Both conditions raise soil temperature, which promotes germination of a new generation of plants, often of species that have been earlier crowded out by more aggressive species. Mineral nutrients are also recycled in the process. The photo on the page shows the differences. Color indicates much about soil conditions and is an important part of soil description. Soil particles themselves display little color. Most are particles of minerals that are nearly white or colorless. Color appears when particles become painted with some coloring agent. These coatings consist primarily of decayed organic material, which is black and darkens the soil, and iron minerals. Iron occurs in several mineral forms, each of a different color, and is the amount of soil oxygen that determines the iron compounds present. With ample soil oxygen, iron is mostly present as the ferric species, or Fe+3, the oxidized form of iron. In the absence of oxygen in waterlogged soil, iron is biologically reduced to the ferrous species, or Fe+2. While ferric or oxidized iron compounds comes in shades that are reddish or yellow, ferrous iron compounds appear gray or even bluish gray or clay. Soil bacteria perform the chemical reduction as they consume carbon in an environment that lacks oxygen. Soil may also display whitish deposits that indicate accumulations of salts and lime. Modeling in the subsoil suggests that the soil is waterlogged for part but not all of the year. A simple description of a soil as dark would not be adequate for a soil survey. Soil surveys rely on a system that provides a precise description of soil color, the Munsell color system of color notation. Using the Munsell method, the surveyor in the photo matches the soil to standard color chips. In conclusion, the various physical properties can affect how well a plant can grow in the soil. Amendments and improvements can be made to the physical properties to increase yield and tilth.